All right, this video is going to be looking at the first section of chapter 3, so section 3.1. We're talking about quadratic functions and models. But before we talk specifically about quadratics, let's talk about polynomials in general. So polynomials, this is kind of a formal definition, but a polynomial has a certain degree, and that will be the degree of the highest term. So this is like x to the n, where n is the highest degree, and then the next term, it would be one less, and then two less than the first one, and so on. So don't worry too much about this, but each of the terms could have a different different coefficient as well. Okay, so this is just kind of a formal way of writing, in general, a polynomial. All right, so let's look at some different types of polynomials. So first one, f of x is equal to 2. Well, this is a constant. No matter what I put in for x, the output is going to be 2. So we call this a constant function. What's the degree? Well, we'd say, well, there's no variable there, right? But we could think of that as x to the 0. So this degree is 0. And the leading coefficient, I suppose if we think of this as x to the 0, then 2 would be the leading coefficient. More often than not, we just think of that 2 as a constant because, we generally don't have that x to the 0 in front. It's just 2. Okay, the next one. F of x equals 5x minus 1. This is what we refer to as a linear function. So linear. That degree is 1. And what is the leading coefficient? In this case, the leading coefficient is 5. The next one, f of x equals 4x squared minus 1/2 x plus 5. This is a quadratic. Its degree is 2. And in this case, the leading coefficient is 4. All right, the next one, the highest degree is 3. Let's put that in first. The leading coefficient, that's clearly 2. What do we call this? This is called a cubic. All right. The next one, the highest degree is 4. It looks a little, like this one looks a little strange too. Let's go back and talk about this one for a second. Square root of 3 is the coefficient of what we call the linear term, but that's fine. It doesn't have to be a rational number. The coefficient just happens to be irrational, which is fine, not a big problem. Okay, let's go on to this one now. So this one is a degree 4 polynomial. The constant is irrational, square root of 5. Not a problem. It's fine. It doesn't have to have a rational number. It could be irrational. So this one is degree 4. The leading coefficient in this case is 1. There is no coefficient out in front, so we know that's 1. This is called a quartic. Quartic. Okay. It's degree 4. All right. Now the next one. It looks like a degree 2, but the problem is, for this to be a polynomial, if we look up here in the polynomials, n is an integer, and so not only an integer, it's got to be a positive integer, and so do all of the other exponents have to be positive integers. So this term in the middle, square root of x, that's the same as x to the 1/2 power. So that's not an positive integer. So this one is not a polynomial. Okay. And then same reason this one is not. The center term here has x to the -1. Again, the degree of each term must be positive. Well, I guess it could be 0 like we saw here, but it can't be negative. Nor could it be fractional like it was in this example. So this one's also not a polynomial. Okay, and so we don't have to worry about the degrees. When we talk about degrees, we only talk about degrees of polynomials. All right, so that was polynomials in general. Now let's talk about more specifically quadratics. All right, we have a couple of forms. We have a standard form. That's the f of x is equal to a x squared plus bx plus c. If it's in this form, we can find the vertex by doing, and you did this probably back in Algebra 1, negative b over 2a. That gives us the x coordinate. So if we take this value, the opposite of b, and divide it by 2 times a, that will give us the x coordinate of the vertex. We would then take that value, plug it in for x, and get the y value for it. So that's how we would take that f of negative b over 2a, plug it back into the function. That's the y coordinate. Okay. If we have it in vertex form, we saw this sort of vertex form when we were doing transformations back in section 2.7. The opposite of this number, which is just going to be h, and then k. And hk is the vertex. So we often will refer to this as the hk form, but it's really the vertex form. All right, so the graph of a quadratic function is a parabola, the shape of which is dictated by the leading coefficient a. A is the one thing that shows up in both forms. That's the same a in both cases. All right, the b and c do not directly give us h and k, but the a and the a are always the same, and that will dictate what shape this thing is, how stretched out vertically or shrunk down vertically this thing is. All right, the graph, okay, so let's see. It has an axis of symmetry, and that axis of symmetry is a vertical line, and it's going to be x equals negative b over 2a, or x equals h, depending on which of the two forms of the equation we're using. When a is greater than 0, the parabola opens up. When the a is less than 0, negative, the parabola is going to open down and have a maximum value. All right, let's try graphing some of these. So this one, I think, because it's in standard form, the easiest thing to do is to look at negative b over 2a. And so we do that. Negative b would be negative 4 over 2 times a, which would be 2 times 1. So that is going to be negative 2. All right, and then what we want to do is plug negative 2 back into this thing. So essentially, what is f of negative 2? That gives us the y coordinate of the vertex. The first thing we really want to do is find the vertex whenever you're graphing a quadratic function, which will result in a parabola. So we want that parabola's vertex. Negative f of negative 2, I plug that in, that's going to be 4, minus 8, and minus another 4, so that gives us negative 8. All right, so then we take that, and the vertex is then going to be at negative 2 comma negative 8. All right, so let's plot that. Negative 2, negative 8, we're down here. And then we know that this is a basic parabola because the leading coefficient's 1. So I'm going to go over 1, up 1, over 2, up, over 1, up 1, over 2, up 4, 1, 2, 3, 4. And same thing over here because we have this axis of symmetry going down the middle. And so that allows me to plot the points as mirrored images of each other. And then if I want to go over 3, I go up 9. So we're down here at 8, 8 more, and then 9 is there and here. Okay, so you want to plot those points. Pretty much, let's fill up the little piece of graph paper that we're given. Sketch that in. And we have our parabola. Okay, so make sure you're clear about where those points are. The vertex is the only thing we really have to find, sort of using algebra here. The rest, we just know the shape. Over 1, up 1, over 2, up 4, over 3, up 9, because we know what a basic parabola looks like. We talked about that in chapter 2. All right, this one. Now, this one's in vertex form. This one's nice. You can tell me what the vertex is directly from this. So the vertex is going to be 1, comma, 0, because it's plus a 0 at the end. If you had to put it in that form, the k would be 0. All right, then the leading coefficient is not 1, so this is not a basic. This one gets stretched out vertically from the vertex. But let's start with the vertex. And also it's negative, so it means it's opening down. So the vertex is located at 1, 0, so it's right here. And if I understand how to plot a basic one, I would go over 1, down 1, because again, it's negative, so we're going down. But now the stretch from the vertex gets doubled. So we go over 1, down 2. And again, the axis of symmetry going right down the middle here. So that means I know I have a point here. I'm going to go over 2, at which point then I go down. Normally I'd go down 4, but now we're going to go down twice that, which is 8. So here. And, you know, that's all we can do. Nothing else will fit. So then sketch that in as best you can, without making it feel too pointy down at the vertex. Arrow is always a good thing to add. Okay. The next one is also in vertex form, so we should be able to say, oh, the vertex is, and be able to write the vertex down immediately. That's -2, comma, -3. So I go -1, 2, -3, 1, 2, 3. All right. Now the leading coefficient is 1/2, so this is not a stretch, but the reverse, it's a shrink. So this one we went over and down double. Now we're going over and up half as much. So I go over 1, up 1 for a basic. I'm going up half as much, so I'm going to go here and here. Again, my axis of symmetry going right down through the middle. Okay. If I go over 2, I normally would go up 4. I'm going to go up half as much. So I'm going up 2. So here and here. If I go over 3, I would normally go up 9. I'm going to do half as much. So 1, 2, 3, 4 and a half is here and here. And then let's go ahead, since we can fit it, let's do one more. If I go over 4, normally I'd go up 16. So instead, I'm going up half of that, which is 8. So here and here. And then sketch that in. So this one is a little wider than a basic. A little wider than a basic. This one got narrower because the leading coefficient magnitude was 2, so it's going to stretch in the vertical direction. This one's a shrink in the vertical direction. All right. Converting now from standard form to vertex form. All right, this is going to seem a lot like completing the square. So I'm going to kind of rewrite number A over to the side so that we have some room to work. So we have f of x equals, and then what I'm going to do is I'm going to complete the square for these. I'm going to move this -5 sort of off to the side, not to the other side of the equation, but just push it aside. So I get x squared plus 2x, and then I leave a space because I'm going to add something there. The -5 gets pushed out of the way. Now, I want to make this a perfect square trinomial. This is a 1, so that's nice. So that means I can take half of this and square it. So that's going to be a 1. The only problem is I just added a 1 to this expression, so I have to subtract 1 to make up for it out here. Okay, so I added a 1 and I subtracted a 1, so I really didn't change anything to that expression. But what that allows me to do is write this as x plus 1 quantity squared minus 6, and now that's in vertex form. So I can very easily now say the vertex is going to be -1, comma, -6. I'm going to plot that point here, -1, -6. There's my vertex. The leading coefficient, whether you look at this one or the new form here. Let's see. So let's see. Let's do this. Let's box that in. This is the vertex form. That's the standard form. A is the same in both. So I know I can just go over 1 up 1, over 1 up 1, over 2 up 4, 1, 2, 3, 4, over 3 up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it just fits, and then repeating these over on the other side. Okay, and then sketch those in, sketch that parabola in, trying not to make it too wonky. Okay, don't like that. Let's do it like this instead. Okay, that looks pretty good. All right, a little wonky there, but you get the idea. Okay, all right, next one. This one we are also going to put into vertex form. Now the problem is the leading coefficient is not 1 like it was over here. So this one's a little bit trickier. So let's do f of x. I'm going to factor a -1/2 out. Now be careful. A lot of students have difficulties with this. I factored a -1/2 out. We don't generally factor fractions out of things. I don't know, this may be the very first time we've done it. So what will the next term be? Remember, when I factor something out, I'm dividing by it. So also the sign's going to change. So it's going to be plus because I just took a negative out. So that sign's going to be plus. But this x in here is now going to be bigger because I just divided it by 1/2, which means dividing by 1/2 is the same as multiplying by 2. So I'm going to have 2x, and just as a check, distribute that back in and make sure you got that center term, and indeed you did. The 4 is just going to get pushed aside, and we want to do plus, and we're going to put something in there. Same thing as we had before, right, as it turns out. So half of 2, because now this is a 1 in front. Inside the parentheses, that's a 1. So that means since that's a 1, this last term is half of this squared, which again is a 1. Now I just added that 1, but its true value, wait a minute, let's see, I need a plus for this 4. The true value of that 1 is not 1, it's actually -1/2. So I subtracted 1/2, I need to add 1/2 to this side over here, all right? Because this 1, I need to counteract that 1. The true value of that 1 is -1/2 because of that -1/2 out in front. If I were to distribute that back in, this true value would be -1/2. So I have to counteract that by doing the opposite, adding 1/2. Okay, so let's see what we've got then. We have f of x equals -1/2 x plus 1, quantity squared, and then 4 plus 1/2, why don't we just say that's 9/2. Okay, so what will the vertex be? The vertex will be -1, comma 9/2. Or, 4.5 when we go to graph it, I guess. So -1, and then 1, 2, 3, 4.5. This is negative, so I know this is opening down. The leading coefficient is 1/2, so we've got to shrink here. So I'm going to go over 1, down 1/2. Over 1, down 1/2. Over 2, down normally 4, but now down half of that 2. 1, 2, and 2 here. Okay. Let's do another one. If I go over 1, 2, 3, I should go down 4.5. So 1, 2, 3, 4.5. So I'm on the x-axis this time. And we could do one more. If I go over 1, 2, 3, 4, normally I'd go down 16. I'm going to instead go down 8. 1, 2, 3, 4, 5, 6, 7, 8. Looks to be about right there. And likewise over here. Okay, because of the axis of symmetry, we could draw that in, axis of symmetry. Okay, and sketch that. All right, so that's page 1. Let's move on to page 2. This is graphing. Some of this should be pretty easy, especially once you get it into vertex form. We did these kind of transformational graphs of parabolas back in section 2.7. So you might go back and look at some of those if you're having difficulties with any of that. All right, let's move on. Write the equation of each quadratic function described. So we have the vertex, and we have the fact that the parabola passes through this point. So let's look at how we can write that. So let's write what we know so far. We have y equals a, and we know the vertex, so we can say x plus 3 quantity squared plus 4. So we almost have everything we need for this parabola, this quadratic function. And you notice I'm using y. You can use f of x if you wanted. We know everything except a. If we knew what the a was, we'd be done. Okay. So what we want to temporarily do is plug the x and y coordinate of the point in for x and y. We did a similar thing sometimes back in Algebra 1 when we were doing linear equations and we were looking for the y-intercept b. We would plug a point in. So similar thing here. 0 equals a, negative 5 plus 3 quantity squared plus 4. So this is going to be negative 2, and we're going to square that and get 4, and then we can move the 4 to the other side. So negative 4, that gets moved to the other side, and then we get 4a. A should equal negative 1. So now let's rewrite the equation we had started here. Now we can substitute back in your a, and so y is equal to negative 1 x plus 3 quantity squared plus 4. Okay, so this is our equation of the line that has this as a vertex and passes through that point. So similar thing for b. Let's write what we have so far. Y is equal to a, which we don't know what it is, x minus 1/2 quantity squared plus 2. All right, and we know it goes through this point. So temporarily plug the x and y in. So we have 7 is equal to a, negative 2 minus 1/2 quantity squared plus 2. Let's move that 2 to the other side. So that's 5. And let's see, this is going to be negative 2.5. So let's call that 5 halves, negative 5 halves. And when we square that, we get 25 fourths times a, and that's equal to 5. So if we multiply both sides by 4 over 25, we should get something like a is equal to, let's see, we'll do 5 times 4 over 25. The 5 and the 25 would reduce, and this should leave us at 4/5. All right. So now let's rewrite the equation that we started up here, but putting just the a in. So y is equal to 4/5 x minus 1/2 quantity squared plus 2. Okay, so similar approach every time you do one of those. All right, find the x-intercepts and the y-intercepts for the following, and the vertex for this following quadratic function. Okay, so the simplest thing is to put x in for, if we think about x and y-intercepts, if I put an x of 0 in, that would be the y-intercept, so that's easy enough to do. If I put 0 in for x, then y is 1. So I know my y-intercept is 0, 1. And then the x-intercept. So that would be when we set this equal to 0. And so we're solving this quadratic. And so I guess maybe the easiest way to do that is to see if this factors. So first thing I'm going to do is I hate factoring with a negative leading coefficient. So I'm going to change this into 3x squared plus 2x minus 1 equals 0. I multiplied through by a negative 1. Now, if we can factor, this will be much easier if it's factorable. So let's try that. So I'm going to say 3x and x. And then I know it's 1 and 1, so let's put 1's in there. And the signs are different, so let's say we want 3x and 1x. The difference should be 2x, so I need this to be plus and this to be minus. So when I solve this for x, this is telling me my x-intercept. So x is equal to 1/3 and x is equal to negative 1. So those are my two x-intercepts. So if I want to write those, I could say as ordered pairs, I can say 1/3 comma 0 and then negative 1 comma 0. Those would be my x-intercepts. My y-intercepts over here, I could rewrite that as an ordered pair as well. 0 comma 1 is my y-intercepts, and those are my x-intercepts. And then the last thing is the vertex. Well, I could put this into vertex form, or I could use my negative b over 2a. Probably that would be the easiest in this case, since they're not actually asking us to put it into vertex form. Just find the vertex. So negative b, that would be 2 over negative 6. All right, so that reduces, let me put equal signs in here. So this is negative 1/3. So that means so far I know my vertex is at negative 1/3 comma something, and I need to take and put 1/3 into that. So I need to figure out what f of negative 1/3 is. And so when I do that, I get negative 3 times negative 1/3 squared, that's 1/9. And then plus 2, minus 2, sorry. Minus 2 times negative 1/3, and then plus 1. Okay, so I could simplify all that. This is going to be negative 1/3, negative 1/3. The 3's would help cancel that, right? And then this will be positive 2/3 plus 2/3. And then let's go ahead and write that 1 as plus 3/3. And so you can, I think you can see pretty easily if you put all that together, we end up with 5/3 minus 1/3, so that's 4/3. So 4/3 is the last part that we're looking for there. So that would be the vertex. Again, the x-intercepts and the y-intercept. All right, let's move on to talk about models now. We already talked about projectile motion earlier this year, and so remember this is the formula if we're dealing with feet. Remember that v sub 0 is the initial velocity, s sub 0 is the initial height, and this s is the height of this object with regard to time. So s is a function of height, and it's a the function is the height with respect to time. All right, so that is, it's not s times t. Remember, this is a function. T is the time in seconds, and we're dealing with feet in this case. The leading coefficient 16 tells us, negative 16 tells us that this is in feet, not meters. All right, so a ball is projected directly upwards from initial height of 75 feet with an initial velocity of 112 feet per second. Give the function that describes the height of this ball in terms of t. So we'll use the same s of t, and so it's negative 16 t squared, and just really asking us to plug in these two values. So it's plus 112 t, and then the height of 75, so plus 75. That is the function that defines this, in this particular situation, the height of the object at time t. All right, after how many seconds does the ball reach its maximum height? So in other words, the maximum height is simply just if we think about, it starts here at 75, and it's going up and coming back down. So we're looking for its vertex. It has a negative leading coefficient. You know, that's a horrible drawing, but should look a little bit more like a parabola, but something like that. So we're just looking, and this problem is asking how many seconds. What's the t value corresponding to that vertex? So we could just use negative b over 2a. That will be the t, or x, in this case, the t value for that vertex. Okay, so that's negative 112 over negative 32. We can reduce that. That reduces to something like 28 over 8. Divide both of those by 4. And then that's reducible to 7 over 2. So 3.5 seconds is when it reaches its maximum height here. Okay? And then what is that maximum height? Well, that's just s of 3.5. So when we plug 3.5 into this function, this will give us the height. And if you take 3.5 and plug it in for t, that function ends up telling us that the height is at 271 feet. Okay, so that is the height. They asked two things: when does it reach its height, maximum height, and then what is that maximum height? So we just simply plug that in to the function. For what interval of time is the ball greater than 200 feet? So presumably, I don't have this drawn to scale, but presumably we have something here at 200. We're looking for the two different times different t times that it is above greater than 200 feet. So we could think of that as an inequality. We did these before. So negative 16t squared plus 112t plus 75 is greater than 200. All right, then we could bring that 200 over. We get 16, and I'm also going to multiply through by a negative so that we don't have to deal with a negative leading coefficient. So we have 16t squared minus 112t, and this will be plus 125 then, is greater than 0. Now, this thing does not end up factoring, so you could, no, this is not divisible. You can't divide through by anything because they're not all divisible by 4. So I'm thinking we're just going to have to plug that in, so we have to find our boundaries using the quadratic formula. So t equals 112 plus or minus the square root of 112 squared minus 4 times the negative 16, which is our a, times c, which is 125, all over 2 times the 16. So remember, we made the leading coefficient positive here. So this should be positive 16. I goofed with that one. So because I multiplied through by a negative, so that's positive 16. And then divided by 2 times 16, or 32. Okay? And if we simplify that a little bit, we get 112 plus or minus the square root. I get 4,544 over 32. So this is not going to get us an exact answer, but if we took and found both of those boundaries, that would give us the two values, and we know between those two values, you don't really have to check here because we can see the physics behind this, that between those two values it's going to be above. And so what are those two values? We end up with something like, if we did a decimal approximation, 1.3 seconds and 5.61 seconds, leaving those as open parentheses, open brackets, because it's just says greater than, not greater than, or equal to. All right, and then when will the ball hit the ground? Well, that's this point over here. Right? It's hitting the ground at what time? So in that case, we can simply set the equation 16. I'm going to use this one up here, but I'm going to go ahead and multiply through by a negative. So 16t squared minus 112t, and then plus 75. No, that should be minus, sorry. Minus 75 is equal to 0. Now, again, that doesn't factor nicely. So as a result, we would have to use the quadratic formula again. T is equal to 112 plus or minus the square root of 112 squared minus 4 times 16 times negative 75. Okay, all over 32. And again, that's not going to give us a nice number. When we were to simplify all that, we'd get two numbers. We'd get negative 0.616, and we would get 7.62 seconds. So this negative is because mathematically, if we went backwards in time, the ball is at 0 back here at negative time. But that doesn't make sense in the context of our problem, so we ignore that one. And so it hits the ground at 7.62 seconds. All right. And that is seconds. Probably good to add that. All right. And then let's look at example 6. So a farmer wants to fence in two areas that butt up against a river. So this is the river down here, and so he wants to fence in these two areas. Let X represent the length of the three parallel lengths of fencing that run down into the river's edge. So he's not going to put fencing here. I guess he figures no one's going to come onto his property because they'd have to wade through the river. All right, so she has 200 total feet of fencing. What is the length? What is the length? Too many lengths in there. There's a typo there. What is the length of fence that runs parallel to the river in terms of X? So this part, right? What is this stuff? How is that represented? Now, we know we have 600 total feet. So what expression could we use to represent this length up here if the total is 600 feet? So that would just be what's left over, 600 minus, take away the 3x. So take away 3 x's from the total, and that will give us this length here. So this is 600 minus 3x. All right, determine the function a of x that represents the total area enclosed by the fence and state its domain. So what is the area function in terms of x? Well, what would be this total area? It's a rectangle, so it's the length times the width, or the width times the length, however you want to call these things. So the area would be 600 minus 3x. It's the total length. We're assuming the thickness of the fence is negligible here. It's essentially 0. Times the other dimension, which is x. And we could certainly simplify that if we wanted to. We could say negative 3x squared, negative 3x squared plus 600x. And then what could be the domain? So how big or how small could x be? Well, let's think about that for a minute. So how big can x be? Could x be 500 feet long? No, because we wouldn't have enough fence to do that, right? So the biggest that x could be is if these three parallel lines were really close together, in which case this length up here would almost be 0 or essentially 0. That would be the low end. Well, we would never really want to do that because then we would have no area to fence in. But if you think about it, we know we can't be bigger than 200. If it was more than 200, it would be impossible to even do. At 200, we have no area, so we know we got to be below 200. So we're thinking of this as an interval. So how small could x be? Well, think about x being really small. Then this is a rectangle that's really long and a very, not very deep away from the river. So I guess it could be almost 0. If 0, then, these things would be essentially nothing, and then this would be 600 feet long over here. Essentially, we'd have no area then as well. But that would be the domain. We'd have to be somewhere between 0 and 200. All right, part C. What dimensions of the total enclosed area would give us an area of 22,550 square feet? So we're just going to say, oh, all right, so the area, 22,550 square feet, is equal to, and then we set that equal to the equation, negative 3x squared plus 600x. All right, so we would want to set that equal to 0, so we would get something like, let's get rid of the negative coefficient here. So let's bring these two terms to the left. So we get 3x squared minus 600x plus 22,550. And that's equal to 0. And that's a quadratic. So again, kind of big numbers. I don't think all of these things are divisible by 3, let's see, 7, 14. No, so this is not divisible by 3. So we can't divide through by 3. So to make the numbers easier, so we simply use the quadratic formula for this. So 600 plus or minus the square root of 600 squared minus 4 times 3 times 22,550. Divide all of that by 6. All right, and then, you really just pick up a calculator and you figure out what those values are. Let's see, we're looking for x. So then, we get x is equal to, and it's not going to be a nice number, but it's an approximate. X could be equal to 50.17 feet, or x could be equal to 149.83 feet. And so if we use those as the x's, we would want to go back and plug in and find the other dimension. So subtract, multiply those by 3 and subtract them from 600. So the other dimension would be 499.49. So these would be the dimensions that would give us this area. And the other one, if we multiplied this by 3 and subtracted it from 600, the other dimension would be 150.51. So those would be the two sets of dimensions that would both give us a square foot area. So one would be kind of a skinnier and taller. One, actually, it would about a square, right? About the same. And then this one, the x is a little smaller, and the other dimension's a little bit wider. All right, what is the maximum possible area that could be enclosed? So if we think about plotting our x value against the area, so if we do like a parabola, and this is x, and this is a of x, we want to know, this is a quadratic, and so this would, again, has a negative leading coefficient, so we are going to have a maximum area at a certain value. Now we know we're between 0 and 200. We know that's the domain. If it's 0, the area is 0. If it's 200, the area is 0, somewhere in between those. So we could probably pretty easily say that, let's write the equation again. We have a of x equals negative 3x squared plus 600x. That's that original function that we had up here. If we sort of do the negative b over 2a to get the x coordinate of that vertex, Well, it shouldn't be surprising since we sort of drew this picture. We know it starts at 0, it ends at 0 over here, so we know this is 100 in the middle, right? Because this is parabolas are always symmetrical. But just to confirm that, we get negative 600 over negative 2 times negative 3, and so sure enough we get to be 100. So now what we have to do is, because they want to know what is the maximum possible area, they're not asking us for the x value that would generate that, so we want to find a of 100. And so we would simply plug that value in, essentially getting the y-coordinate of the vertex, right? So we put 100 in there, we get negative 3 times 100 squared, so that's 10,000. Not 10,000. Yeah, 10,000. Sorry, it is 10,000. And then plus 600 times 100, and so that's 60,000. Okay. So if that's going to be negative 30,000 plus 60, so that is 30,000 square feet is the maximum area that you could get. Okay, so this homework is due next class. All right, remember that the multiples of 3 is what that x3 stands for. All right, A stands for all, don't forget that. So do all of that in that range, all of those in that range. All right.